So I wanted to talk now in detail about sort of the mechanism that we're using to do the memory validation. So as we mentioned earlier, we're effectively doing at most one memory transaction per execution cycle. And honestly, if we don't have a specific memory transaction, we just do a read of memory address 0 or whatever as a default. So there's always one memory transaction per cycle. So there are two sets of columns. They're both in the data section. One of them is the memory operations, and those occur in program order. And so there's a sort of cycle of which logical cycle this is, and that just moves forward, monotonically, and there's a constraint that always moves forward monotonically. And then there's basically the address, the data, and a read-write flag, which of course have constraints that are hooked into the rest of the circuit. So that basically
just real quick, Jeremy,
yep.
if you do
I can do this.
If you do this, you can
there you go.
Do a pointer thing that everybody will see, and hopefully
there we go. Yeah. So this is the cycle. This is the normal ordered. So this is all happens in cycle order. And so what we're saying here is, okay, at time 0, I'm going to do a write to address 3 of the value 17. And then at time 1, I'm going to do a write at the address 7 of the value 3. Then of course, later, I'm going to read from address 3, and I'm going to read back 17, or at least I should, assuming memory is valid, right? So what happens is during the initial program execution, we generate these columns, and we just model memory externally, right? Then what we do is after execution, we do a sort of all of the values in here into this sort of verifiers, this sort of second copy of the memory transactions. But these are, instead of being sorted by cycle, are sorted by address first and cycle second in lexicographic sort order. What that means is that all of the memory transactions that occur on the same address are all now located next to each other, and all of them are in proper cycle order. At which point, basically, it's possible to quickly verify the validity of the memory transactions. Oh wait, you know what? This should actually be a 1, shouldn't it? Yes. Oh shoot, I guess I can't edit this document while I'm doing this. Sorry, this is a 1.
I remember that.
This is a 1 right here. Yes. So what you see is we write 17, and then we read it twice, and then here we write 2 different values and read it. And interestingly, the requirements for the verifier are basically written here. They're actually fairly simple. If the addresses are the same, then we have to verify that the cycle is moving forward, and if it's not a write, we have to make sure that it matches whatever the previous value was, and then also that if the otherwise, if they're switching between addresses, the only thing we care about is the addresses are going up. You will note, by the way, that this allows an initial read prior to a write to return any value whatsoever, which we actually take advantage of. Basically, reads of values never written are in fact undefined, and we use that actually as a way to interact with the external world. So basically, in addition to so besides the set of constraints that represent the verification of the resorted versions of the address, we also have to prove, of course, that these 2 different tables are in fact permutations of each other. Which we do using the sort of PLONK permutation argument, where we basically commit to the entire state of the data trace Merkle tree, and we use that and the Fiat-Schmier sort of mechanism to then pick a number, a set of ways of. I won't go through the PLONK argument in detail. I'm sure people have read the paper, and if not, it's a great paper.